Which ones did you think were exothermic?
Those are tricky because a lot of, you know.
Yeah, that's tricky.
Yeah.
Yeah.
Because I thought I knew, I'm like, oh, exothermic, was it water something?
Those are the tricky ones, right?
I know for sure E.
So what do you know for sure?
E, I think.
Why E? So what does it mean if for something to be exothermic?
Release energy, so I think B.
Release energy. So something that releases energy, gives energy away from the system. How would we experience something releasing energy? What? Not exactly. Actually, it kind of depends on which part of the process. Yes and no. That's more complicated than that.
Steam in the air, like vapor in the air, like heat.
Yeah, I mean, exothermic, if something's exothermic, it's giving off heat. So you're getting the heat from that thing. So I think maybe one good example of that then is D, natural gas burning. Something burning is always going to be exothermic because it's giving off heat, right? The burning is giving off the heat, and that's why it feels hot to us. The water stuff gets a little bit tricky. So then E is the opposite. It feels cold because it's endothermic. It's sucking the heat in, which makes it feel cold. So the water ones get tricky because we don't really experience, or we don't think about experiencing water melting or freezing as like giving off or taking in heat, really. But here's how I think about it when I get confused about this. If you have an ice cube and you want to turn some ice into some water, what do you have to do? Do you have to add heat, or does heat get released? You have to add heat, right? That's one that we all kind of experience. So ice plus heat melts into water. Okay. So then what must be happening in the opposite direction? If you take water and you turn it into ice, the heat has to leave, destroy heat. So either the heat gets taken in to melt the ice, or the water becomes ice and releases that heat. That's that heat of fusion, that 80 calories per gram heat of fusion. So then water freezing is another exothermic process. Ice melting is the endothermic process because it takes heat in. All right. Similarly, we can talk about water going to, I don't know how to draw water vapor. Let me get little dots. You know what I'm talking about, right? Water vapor. So liquid water going to water vapor, does that take heat in to do that, or does it give heat off when it becomes water vapor? If you want to boil water, do you have to put heat in, or do you have to take heat away? Heat in, right? So same thing, same direction. Water plus heat gives you water vapor. That's 540 calories per gram of heat required to turn liquid water into water vapor. So the same thing, the opposite is going to give up heat. The opposite process will give off heat. So the other exothermic process here is water vapor condensing, which then gives off that heat. No, if you add heat, it's endothermic. So then everything in this diagram, everything going this direction is endothermic, and therefore everything going this direction must be exothermic.
So I guess even, I mean, I know it's an endothermic process and an exothermic, but even if it's like not hot out, it doesn't matter. The process in itself is exothermic.
Right. Right. It's what's happening with the actual molecule itself. So you can also think about it from a small molecular level. Ice has water hooked together pretty tightly, right? When it melts it, that kind of gets ripped apart. So it takes energy to rip those things apart. Water goes to vapor, rip that apart again. Then when you condense that water vapor, the molecules are coming together. That's a more stable situation, so that extra energy is released. And that's what makes it exothermic. The reason that it's so tricky is like you said, the temperature that we think about these things happening doesn't necessarily apply. So like, yes, water turns into ice at a low temperature when it's cold, but that doesn't mean it isn't releasing heat. Yeah. All right. So the way I'll grade this is if you get them all, you get 2 points. If you get some, you get 1. If you get some, but also some wrong ones, probably not. We'll see. All right, so how about the next one? Some mixtures, some definitions here. What would be an example of a homogeneous mixture?
Gasoline?
Kool-Aid, gasoline, sure. Is it 8? No, it's ADE, isn't it? Kool-Aid. I don't actually know. Is it what? Is it? Because like lemonade is ADE, right? I guess they spell cool wrong, so they might as well spell aid wrong. All right. So Kool-Aid gasoline. Don't drink Kool-Aid gasoline. That sounds like a bad idea. But yeah, how do you know those are homogeneous mixtures? Right. You can't see the individual domains inside the mixture.
What if you say concrete from this?
Sure.
Is blood one or
Yeah.
water?
Water doesn't work here because why doesn't water work? I didn't hear who said that. But water is a compound. So what's the difference? How do we know that water is and not a homogeneous mixture? How do we differentiate that? What? Yeah, both of those are correct. So you've got water is its own chemical compound. It is elements, atoms bound together, and it's a pure substance. So if you have a sample of pure water, every single bit of that water is H2O molecules. There's nothing else in it. So that makes it a pure compound. The only way you can break water down is by chemical means. You can do chemical reactions to break the hydrogen and the oxygen apart, but you can't do it by physical means like evaporating something or filtering something.
Is it okay with the sodium chloride too?
Sodium chloride would be another compound. But salt in water, that would be up in the homogeneous mixture because now you've got different stuff altogether. Other compounds, I mean anything that is a pure chemically bound substance, so sugar, glucose, any of those salts we talked about last class that we were naming, those would all be pure compounds, any of that stuff. All right, what about a heterogeneous mixture? Sandwich, okay. Yeah. Anything that you can see the different parts of. So a sandwich, somebody's in my other class said sand and water. You can see the sand and the water definitely in different parts. Yeah. Anybody get anything else, or was it all sandwiches?
Subway.
Yeah, everybody smelled Subway coming in and just said sandwiches. Marble? Yeah, absolutely, because you've got clearly the different domains, the iron-rich parts that are darker black, and then the whiter parts in the marble. Yeah. All right. Heating curve. We've seen some heating curves before. How do you find the boiling point of this substance? It's D. So what is the boiling point? Yeah, about 60 degrees C. If you went with a piece of paper really carefully, maybe you thought it was 58 or 59 or 63, whatever you put, something around 60 is fine. If we think about our measurements back from the really early chapter, because these ticks are only in 40s, we really can only estimate that within maybe plus or minus 10. So whatever you said that was something around 60 is fine. All right, so how do we convert that to these other temperature scales? All right, so to Kelvin, we add 273. So 60 plus 273 is 333 kelvins. And what about to get to Fahrenheit?
1.8 Celsius.
So we're going to multiply it times 1.8 and then add 32. Anybody remember what we get for that? I forgot the number. 1. No, it can't be 200. Maybe 140 something? 140? Okay. All right, at which part here is the substance a solid? A. All right, that's the solid being heated up. At B, is part solid and part liquid. Both exist at B. And then this was probably the hardest question of the whole thing. Definitely requires a little extra thinking. Assuming the graph is to scale, which state has the highest specific heat? Why the gas?
Steam is twice as hot.
Because it's hotter? All right. What is specific heat? How do you define specific heat?
The difference in temperature, well, is the mass times the difference in temperature and
Keep going. Anybody else? What is specific heat? You don't have to give me like an official mathematical definition. Just what does specific heat tell us?
the amount of heat it takes to.
Yeah, the amount of heat it takes to increase the temperature of something. That's what it is. So with water, we talk about the specific heat as 1, because it takes 1 calorie to make 1 gram of water go up 1 degree C. And then other things have different specific heats. So specific heat is just a measure of how much energy it takes to raise the temperature of something. All right. So we've got 3 different states here. We've got a solid, a liquid, and a gas. So the question is, of those 3 states, which one takes the most energy to raise the temperature? And how can you describe it?
Yes, because it's longer.
What? Yeah. Sorry, what did you want to say? The longest line? What were you going to say?
I said yes because it takes longer, right? It takes more.
Yes. Well, let's look at this then. So the heat added is on the bottom. So let's say let's look at the same amount of temperature. So if we go from 100 to minus 60, that's 40 degrees, right? So that's the same as like any of these, 60 to 20, or so there's 100 to 60, there's 60 to 20 in liquid, and then in gas, 60 to 100. See that? So that's the same temperature range for each phase. Which one takes the most energy? Which one covers the most space horizontally? The solid. So it takes the most energy to raise the solid 40 degrees. It takes less energy to raise the liquid 40 degrees, and less energy to raise the gas 40 degrees. So you see that distance there? The most energy to raise at the same amount of temperature. And remember when we talked about this in class, we talked about water versus something like aluminum. It takes a lot more energy to heat water up from one temperature to another than it does for something like aluminum. It takes a lot less heat, a lot less energy to get that aluminum up to the same temperature. So we say that water has a higher specific heat.
So we have the solid.
Yeah, so the solid has the highest specific heat. The lowest specific heat, it's a little tough to judge, but I think C is probably because it's the steepest line. So it takes the least amount of energy to heat that one up. So that one's tough. That takes a little thinking. I mean, they all take thinking, but this one takes a little more beyond what we may have already thought about. All right, so quiz number 2. Got lots more. Don't get too upset if this didn't go well.
That's what you said the first time, yeah.
No, this is not good.
Yeah, so you still got lots and lots of time. One thing I've noticed in this class, everybody kind of has their favorite chapters that come along, things that work nicely for them. Just kind of depends on what gets into your brain well. So, you know, if this isn't yours yet, that's fine. You can work hard, do some problems, power through it. But remember, the important thing is the exam on Tuesday. You've got to be prepared for that. So to that end, I posted my actual first exam from last year. So you can go look at that. It was the actual exam I gave on the same chapters in the spring. So that's posted. You can see kind of the layout. Obviously, the big danger to using that as a study guide is that an exam is just a snapshot. It's just an example of some questions that can be asked. So if you use that as your study guide, you go through every single question on the exam and you think, okay, I got this. You probably kind of don't, because that's only a select group of questions. So use that to test yourself at the end. Use that to check. Use that to see the format so you're not scared when you come in and think like, oh, I don't even know what this test is going to look like. It's going to look like that. The questions are going to be broken down in about the same categories, the same types, but those aren't going to be the questions on the exam. So also keep working on the homework problems.
When are you going to post the next homework on the transcript?
Should be there.
Okay, because I checked last night.
It wasn't, yeah.
Really?
Yeah.
I can't remember it was.
Chapter 4,
Yeah.
the ion, atoms, and
I'll
elements.
double check.
It should have been posted, I don't know, several days ago, end of last week. Maybe it's like down near the bottom. Maybe it's out of order or something. You said you saw it, right? Yeah, because it's not actually due until the next week, because I want to make sure that studying for time for studying and all that. So you may see it on a later due date.
The exams are for 1 through 4?
2 through 4, 2, 3, and 4. Yeah.
On what book?
2 through 4 in the new book, which I think is 1 through 3 in the old book.
Yes, next Tuesday.
Next Tuesday during our lab time. So we'll come here first. We'll have time to answer questions, whatever anybody wants to talk about. We probably won't really get into new stuff on Tuesday because, I mean, nobody wants to try to learn new stuff when you've got an exam coming up in half an hour. So we'll just use that time for questions and for study and for whatever, and then we'll go upstairs and do these.
Can I just ask a question?
So what we did on Thursday, on Tuesday, is that going to be part of the exam too?
The naming?
Yeah.
No. The naming is in the next time. So you got plenty of time to work on it. Yeah, it'll go up through, the last chapter that we're doing is the one that has all the atoms and neutrons and protons and electrons and that kind of stuff.
That's pretty much.
But that's on the exam. The naming comes into the next chapter,
That's
which
why the
is...
homework's not due. That's what you were saying? Until next time? Or?
Well, no, because both... There's homework for chapter 4, which is on the exam, but the homework is not due until after the exam, just because if somebody doesn't need that much work on that chapter, I'd rather you spend that time on other stuff that you do need that work on. Other questions? All right. So going on then, we looked at some of this naming. Is there other stuff that you want to work on now besides the naming? Or should we get this part finished up a little bit and then wait for Tuesday?
I'm still hung up on the exothermic endo experiment.
Okay.
Because, like, water freezing, I didn't think that would be an exothermic. I'm still trying to catch up with that.
Okay. Let's look at that one more time.
So this is what I'm doing.
Right. It'll be on the next one. It's not this one. And we'll probably have a quiz on this not next week, but the week after. All right. So let's say we have 1 gram of ice. Very small little ice cube. And it's at 0 degrees C. So you can have ice at 0 degrees C. Even though that's the melting point, if you can restrict the amount of heat, you can have ice that's just 0 degrees C. If you want to turn that ice into 1 gram of water, at 0 degrees C, how much energy does it take? So you're not changing temperature, you're just changing from ice and water. What do you have to do?
If it does 1 gram times the 80, is it
Yeah, the 80. So it takes, you need to give your ice 80 calories of energy to then turn it into water. All right. If we look at that on a graph, let's say this is energy on the y-axis. So lower on the graph is low energy and higher on the graph is high energy. That means that going from ice to water, we start down here somewhere, and then we end up here, because we've added 80 calories. So let's say that this distance then is 80 calories. We started at low energy with the ice, we went up to high energy with the water. Now energy is always conserved. You can't create or destroy energy. It's not in a chemical reaction. So, or a physical process like this. So if we then want to turn this water back into ice, 1 of ice, and again we're still not changing temperature, something has to happen to that 80 calories of energy. What happens to it? It's removed, it leaves. So now our 80 calories come out when the ice is formed. So the energy of the ice then goes back down to where it was before. And that extra energy goes out into the surroundings. That's why this part of the process is exothermic, because energy is released. Energy comes out of the substance and into the surroundings. And that first process then, endothermic, because we had to put that 80 calories in to get that ice to turn into water. The reason that this is, or one of the reasons this is confusing, is because of the temperature. This happens at 0 degrees C, so we think, oh, this thing is cold, and if something is cold, it's endothermic. That's not really true. If something becomes colder because of the chemical process, that's endothermic, because it's sucking in the heat from the surroundings. But you can just, you can have cold. You can have a fire outside in the middle of winter. It's still an exothermic process, even though it might feel cold around or something. So the absolute temperature of the surroundings doesn't matter. That's what's happening in that process. And this is a pretty general thing. So it's not just for most substances. Melting and boiling are endothermic processes. Freezing and condensing are exothermic, depending on how much energy you need to put in.
Freezing is not what you said?
No, freezing is exothermic, see, going from water to ice. The way I remember it, as I said in the quiz, I think about, okay, you've got to add heat to ice to get it to melt. So if I can keep that one straight, the other direction has to be the opposite. So if I can get that putting heat in melts the ice, then I know that if we unmelt the ice, or freeze it, we have to get that heat back, and that's exothermic. So that's how I think about it. All right, let's look back at some of these names. Let's go all the way back to our rules to kind of remind us here. The rules are, if you remember, the metal name stays the same. So you look up the metal on, if you're trying to come up with a name from a formula, you look up the metal on your periodic table, and you write down the name just as it appears on the periodic table. So if the periodic table says nickel, you write nickel. If it says sodium, you write sodium. Nothing changes. The non-metal, the other part, if it's just a single element, drops its suffix, the end of the word, and you replace it with bromide, Oxygen becomes oxide. Doesn't matter what that end of the word is. You get rid of it and you put in "ide." And then you put them together with the cation first. So that's basic naming of ionic compounds. So remember that from Tuesday? So let's try another one before we get into the trickier stuff with the numbers. So if I give you the form SRO, see if you can come up with a name for that one.
What is this?
SR is, anybody look it up?
Yes, sure.
Strontium. Right. So this would be Strontium Oxide. Strontium salts are used in a lot of fireworks. When they burn, they emit a bright red. I think we used strontium in the flame test. Was that one of the red ones in the flame test, or we didn't have that? It's a little bit poisonous. We might not have used that one. I don't remember.
It might kill you.
Yeah, just a little bit.
Yeah, we did, no, we
We're missing it for kids, so.
NO, SRNO.
Yeah, so we used strontium nitrate to burn, and it made a really nice red flame.
nice.
Right? Yeah, and the red colors in fireworks often come from strontium salts. They're fairly stable.
Can we go over again after this, like a little bit about like when we're naming it, or how to determine like the.
We'll do next.
Because I'm so confused with the whole balance thing.
Okay. So let's go the other way, which is starting to address your question. If you're given a name of this type, you have to come up with the formula for that name. So let's go with let's stick with blue, please. Barium chloride. Right, this is one of the compounds that you used in the flame tests. Also kind of gave a greenish, yellowish, greenish color, I think. So barium chloride, what do we need to do first to go backwards? What would you do first? First, we got to just find the symbols. So we got to look up the symbols. What's the symbol for barium? Ba, and chloride is Cl. So we've got barium, we've got chloride. Now, do we just stick them together and we're done? No, because we don't know what their charges are and how many of each we need. So the next step is to figure out what the charge is on each ion. How do you get that? Yeah, we have to look at the valence electrons. So how many valence does barium have? 2, which means what's likely its charge going to be? Plus 2, because it can lose those 2 valence electrons and then have a full next shell. What about chloride? You probably might know chloride because we've been using it a lot, but how would you figure it out if you didn't know? Yeah, so how many valence electrons does chloride have, or chlorine have? 7. So what's it likely to do shell? Grab 1. So if it grabs an extra electron, what's its charge become? -1, because now it's going to have 1 more electron than the protons. Ones that can change, like in the middle? Yeah, we'll get to that next. All right, so then how do we put these together into a complete formula?
We have to balance them out.
Okay, how do you do that?
We need 2 chloride to put 1.
Right, the overall charge, overall positive charge has to equal the overall negative charge so that the compound is neutral, which means we need 2 chloride ions for every 1 barium ion. The barium's 2 plus, the chloride's 1 minus. We need 2 of those, which means that our complete formula will be BaCl2. The little 2 tells us we need 2 chlorides for every 1 barium. All right. Do one of the another type now. Similar, but now we're going to deal with some of these metals that can change their charge. They can have different charges. So let's go with platinum 4 oxide. So this is going to be an ionic compound between which 2 elements? What are the symbols here? PT and O. Now we need to find the charges again. What's the charge on platinum? Unknown based on the electrons, but it is known based on the name. How does the name tell you what the charge should be on platinum? The 4 that comes after the platinum tells you the charge, the positive charge on the platinum. So the fact that it's platinum 4 oxide means that that platinum must be 4 plus charge. So that tells you it has to have a 4 plus charge.
Well, most of them, you know what I mean? I'm assuming that one is combined with like another non-metal element to have like a Roman prefix.
If it has multiple possible charges, then it must have the Roman numerals.
Right. Yeah, that's right.
Yeah. If it doesn't have different possible charges like strontium or barium, then we leave the Roman numerals out. So then what's the charge on oxide? -2, how'd you get that? Right, 6 valence electrons, so we get 2 more, and we're at 8, so that gives us a -2. All right, so then how do we put these together so that the overall charges balance out? Right, we need 2 O2 minuses for every 1 PT4 plus. So this gives us an overall charge of -4, and then that's an overall plus charge of 4. So 4 and 4 balance. Our formula then should be PtO2. Okay. All right, now you try one. Cobalt 3 oxide. What's the symbol for cobalt for those of you who don't have a, what is it?
CO.
CO. Right. All right, you got this one?
Yeah.
What do you think?
CO2O3.
Nice. Good job. How you came up with that? Anybody want to
Well, since it
take us through the logic?
has a three positive, three.
All right, so cobalt has a positive 3 charge. We knew that from the Roman numeral 3 here.
And then oxygen has a negative 2 charge.
Yep.
In order to balance them out, you need, if you add another one that's 4, so you need to balance them out, so you need 2 of the cobalt. That equals to 6, which means you have to add 2 more of oxygen to add up to that same.
Right, so now we've got 6 plus total is 6 minus total. And that works. All right, great. Let's try one the other direction, where I give you a formula, you come up with a name. CrO3. What's the name for Cr?
Chromium.
Chromium.
Sorry.
Come up with the name. Name.
Chromium, you said?
Chromium.
Chromium.
Chromium, especially in particular forms, is very, very dangerous, carcinogenic. It's a big, dangerous pollutant in the environment because it's used a lot in making steel. If you've heard of chromed steel or something like that, that comes originally from using chromium. It's still an additive, and in steel it's not dangerous, but when it gets out into the environment in the process, then it can cause some problems.
Is there a limit on
Well, yeah, that's a good question. I don't know if anybody heard this. The question was, is there a limit on the Roman numerals? Is there a limit to how high it could go? What do you think?
No.
No? Actually, there is. There is a limit. And what do you think the limit might be? Yeah, 7 is the highest. Because if you lose 8, suddenly you're changing your, you're going back to the other shell, right? You're losing all the electrons. Nothing's going to do that. So the highest numbers that we know about go to 7. I mean, other than probably some really extreme situations. We should also say that when we talk about these compounds with these really high numbers, they're no longer actual charges. They're something that we call oxidation states, and we'll maybe get into that later. But it does mean that they're missing electrons, but it doesn't mean that they're isolated charges, because a charge that high would be way too unstable to exist. So, what do you think about this? Anybody want to give this one a shot? Chromium 6 oxide. Okay, anybody anything else? So we all got chromium oxide, it sounds like. And the question is the Roman numeral. So we've got 6, 2, 3, various choices. There are other numbers. Anybody want to throw out a 5 or a 1 or 8? There's no Roman numeral? How do you know that?
They could have 6 valence, and so 2 for each oxygen.
All right, that's interesting logic, but it's not correct. I like the thinking. It just didn't quite go to the right place. It's like, you have a really good run or something that doesn't actually get you to where you wanted to go.
Why wouldn't it be chromium trioxide? It's 3 oxygens, right? I mean, why
Right.
wouldn't it?
But that's a really good question. Why don't we just name them based on the number of other things, like chromium trioxide? The answer is we do name things like that, but those types of compounds are called covalent compounds. They're hooked together in a different way, and we're going to talk about them next. So when we have a metal and a nonmetal making what we call an ionic compound, which I guess I should say, especially since this is on the internet, CrO3 is not actually an ionic compound, but it still works to talk about it this way. But these other compounds, we will name them like that. Right? It's these metal, non-metal combinations. We don't use that language.
If it's a metal, non-metal combination, it's always going to be an ionic bond.
It's going to be named that way anyway, yeah. You want to change yours to 6? Okay. All right, so let's look at it. It is true that chromium does have different possible numbers that we can put in here. In fact, it's one that has a lot of different possible numbers, depending on what's with it. It is in the middle there. It's element number 24. So we have to look at the ions that we do know to figure out the one that we don't know. In this case, the one we do know is oxide, because oxide is always what? Yeah, -2. And so if there's 3 oxides, right, that's what the formula tells us, then what does the charge need to be on the 1 chromium to offset that? +6. So we call it 6 oxide. And it's good that people said that, because this is the most common error in this type of naming, is to use the Roman numerals to say something about the number of atoms instead of the charge. The Roman numeral only refers to the charge on the cation, the charge on the metal ion. Always does. It doesn't refer to the number of things.
What if we forgot to write the Roman numerals and just did 6?
Well, look up 1 through 6. But if you just do like 6 lines, all right, I get the idea. That's fine.
If it's a 1 and 5, it's a 5, right? It's 1 and then the V.
If it's 1 and then a V, the V is 5. So if it's IV, that's 4. So that's 1 less than 4. If it's VI, that's 1 more than 4. So that's 6. Have you ever noticed how clocks do Roman numerals a little bit differently? I don't know if you've ever noticed this. If you look at a clock that has Roman numeral faces, the 4 is always 4 lines instead of IV. Yeah. Yeah. I think it's just like it's better with symmetry or something, but it's always been like that. So, I don't know. Weird. Maybe it's copyrighted? That's an old copyright. Okay. So, this is going pretty well. Should we get trickier? Should we get harder? Should we just look at this a little bit more? Why not? All right, we're going to stick with ionic compounds for now. But what we're going to change is the counter ions, and specifically the negative ions. You may notice that, or you may have noticed, that in all of our examples, the anions have something in common. And something in common is they've always been made from just one element. So just oxygen, or just chlorine, or just sulfur, or something like that. But from what we've done in lab, we know that sometimes those aren't the only kinds of ions. Remember any of the compounds from lab on Tuesday? What were some of the negative ions in the solutions from Tuesday? You remember?
From the formulas that we used?
Yeah.
Well, we have.
There's a ton of them.
There's like barium chloride, that was one that was replaced with.
Yep. And the other ones were all nitrates, right?
Yeah, nitrates. Almost all of them actually have nitrates. Except for that one.
So we had a thing like this. Lithium nitrate, that was one of them, right? And this, if we're using the rules and all the techniques that we've just been talking about, this kind of doesn't make any sense. If we say, okay, oxygen is -2, oxide is -2, nitride is -3, that's a whole lot of minus, and we know lithium's only 1, but that doesn't even seem like it should balance. Also, it has this totally different name, nitrate. That doesn't fit anything. It's not nitride oxide or something like that. It's this whole different thing. And what this is known as is a polyatomic ion. meaning an ion made out of multiple atoms. So that whole thing, that NO3, is one ion. We write it like this, NO3 minus. It's a 1 minus ion, and its name is nitrate. And it is not separable. Not in the way of just dissolving this. The nitrogen does not separate from the oxygen when you dissolve this in water. When you dissolve this in water, the lithium separates. So you have lithium plus, regular lithium ions. And the nitrate is separate. You have nitrate ions. But the N's and the O's don't actually break apart. We can draw, we'll get into chemical structures later, but we can draw that this is actually connected in this way with these covalent bonds that we'll talk about later. So this thing kind of stays together, and the whole thing together has a -1 charge on it. That's called a polyatomic ion. So when we're trying to figure out the balance of charge here, we actually use this all together as a -1 ion, and it's together with lithium plus. So you've got 1 plus, 1 minus, it balances out.
Where does one have to
We'll get into that because it's sharing electrons in a different way. Yeah, it's called a double
So
bond.
we will always calculate that, we're not going to try to separate the end.
We're not going to try to separate the ends, no. So if you see more than one nonmetal behind your metal, you're now dealing with a polyatomic ion. Now there are some compounds where you have multiple different kinds of ions, but we're not going to get into that in this class. So if you see multiple, that's what you're going to look for. Is multiple nonmetals.
How can we figure out if it's charged then, before that those two together?
Ah, that's the question. And unfortunately, I don't have a good answer for you.
Because we don't, it's not like we have here.
It's not on the periodic table. So what do you have to do? You have to just know some different ones. I never like to give that answer because I like you to be able to figure stuff out. But in this case, you got to just know them. So there's a list on Blackboard. Don't start studying it yet. Wait till after the exam. But after the exam, you can go into chapter, whatever this chapter is, ions and molecular compounds. And you can look at the specific polyatomic ions that you need to know. And you just print yourself out a little list, carry it around with you, learn those. Just like other things, as you do more problems, as we work with them in class, it'll become kind of in your brain. But there will always be a couple that you always have trouble remembering. Everybody does, and those are the ones you'll have to work on. But let me give you some examples of some different ones. So you can kind of organize these in any way you want, by charge or by atom. So we've got NO3, which is nitrate. We've got OH minus. Anybody know what that one's called? Yeah, this one's hydroxide. We have CO3 2 minus. Anybody know what that one's called? Yep, this one's carbonate. We've got SO4 2 minus. Anybody know that one? Want to take a guess? Sulfate. This one, I'm guessing nobody's going to know this one. This one's acetate. There's a couple more. I don't think this is everyone on the list. One more. There's not a whole lot you need to know, but there's a few of them. Chlorate. Well, there is. I mean, there's a huge list in your book, and if you were to take, go on and take regular general chemistry, Chemistry 121 here at Harper, you'd need to know this huge list of them. If you took chemistry in high school, maybe you had to memorize a big list for a special quiz. For this class, we're just going to say, okay, here are the really common ones that we're going to use all the time. These you need to know, and we're not going to worry about all the other ones. Oh, and then there's a positive one. There's only one positive one that you need to know. It's NH4 plus. And that is ammonium. Doesn't look anything like N or H. Or, yeah, so totally weird name for that one. And let's see what other ones. A couple more. Again, I'm not sure this is the same list that's on Blackboard, but these are some common ones that we'll use. HCO3, 1 minus. This is going to be, this has two names, either hydrogen carbonate or bicarbonate. CN 1 minus, cyanide. So we'll see if some other ones come up, but these should be a good list for now. Now you can see there's no real rhyme or reason for this. And if you go on in chemistry, you'll learn about how there is actually some rhyme or reason here, but I think at this point it's just way easier to remember these. Some of them have different numbers of atoms, one or the other. They have different charges. So organize them in a way that works for you. Make some little flashcards, whatever works well to get these things known. There's no good way to just figure it out from looking at the periodic table. There are some ways, but I'm not sure they're any more helpful than remembering them. The good news is, once you know these, the naming isn't any different from what we've been doing. So if we have, let's say, NaHCO3, the way we name this is just like how we named it before. We put the cation first, the anion second. If the cation has different possible charges, we put parentheses and we put the number in there. Same stuff we did before. The only difference is now we're dealing with this whole ion that we have to either know or look up on a chart. So what's the name of this whole compound? Right. So this would be, that's baking soda, sodium bicarbonate.
So in this one, we don't have to try and figure out how many of each of them there are because there's only going to be one metal?
Not exactly, no. So let me show you that example. Let me show you an example of that. So you'll notice that some of the formulas from the lab on Tuesday sometime, that some of them have some other things going on. Like the one we used for the red flame test that we just talked about earlier, strontium nitrate. So the name is strontium nitrate. And to put together the formula, we use the same procedure as we did before. We take strontium, which is Sr, and what's the charge on that? +2. And then we take nitrate. And what's the formula for nitrate? NO3, and what's the charge? -1. So we put them together like before, but you'll notice there's a mismatch here, right? We've got 2 plus and 1 minus. So we actually need 2 whole nitrates for every 1 strontium to get them to balance out. So the overall minus is the same as the overall plus. The way we write that formula is with parentheses.
Wait, how do we know that NO3 is -1?
We just know.
Somebody was saying earlier that
You just have to remember the charge for each ion along with its formula for the polyatomics.
I think because it's just like this.
Oh, so it was already in there.
Yeah.
Just missed it.
So the way we put the formula together then to account for the 2 whole nitrates is to put them in parentheses like that. We can't say SrNO3 2 because that kind of looks like SrNO32, and if there weren't a 3 there, that would really mess it up because it would look like you were just changing the oxygen. So you need the parentheses there to adjust that, to adjust the charge accordingly. All right, so that's the end for today. We'll come back to this after the exam. So happy studying. Hope it goes well. Let me know if you need anything.
Yeah, because, okay, so to summarize,